Assalamu alaikum. In this lecture, we are going to discuss the remaining two techniques for quantitative approaches of forecasting. So we also are going to learn how to develop the seasonal index and how to deseasonalize the data. But before moving towards the today's topic of discussion, let's have a brief recap of the previous lecture. In last class, we have learned about the forecasting techniques and its approaches, which includes the qualitative and quantitative approach. For this chapter, we are only focusing on the quantitative approaches, we already covered two techniques, which includes the moving average and weighted moving average. Now let's move on to the third technique, which is a linear trend. If you remember, in chapter 3, we already studied the linear equation and the introductory concepts for regression and correlation. So here I'm going to draw a line, and these are some data points given, and a line passes through right middle of these data points. So this line have a particular equation, which is y is equal to a plus bx. So if you can see that the linear trend equation and the linear equation are almost similar except one difference, and that difference is this hat. Y hat is basically the projected value or expected value, or you can say the forecasted value of a variable of interest. Variable of interest is basically this response variable or the dependent variable of this equation. Likewise here, all the components are similar except this hat. So this hat is basically showing that it is not a simple linear equation, but it is a linear trend equation. A is showing the intercept of the line. Intercept is basically the estimated value of y at time is equal to 0, or you can say the initial value of the y. B is basically the slope of the line, which is which measures the change in dependent variable for each unit change in independent variable, or you can say it is basically measuring the changes occur in dependent variable due to 1 unit change in independent variable. So beta is B is the slope of the line, and this t is showing a independent variable IB. This t is basically showing time as independent variable, and this x is also showing independent variable, or it can be any independent variable in regression equation. T, any value of time coded that is selected. T is basically the years or the numerical coded values where all the sales data points are given. We will see in the next slides. So let's move on to the next slide. So here is the linear trend plot. Blue line is basically showing the sales data, and pink line is showing the trend line. And these are the sales on vertical axis, and horizontal axis shows the years and the codes for each year. So years are basically coded on these numerical values from 1 to 9. So this is a straight line fitted on sales data. So if we are going to draw a line on a straight data, on a sales data, so probably 3 people draw a different line without using any particular method. So that method will involve a subjective judgment. So To overcome this drawback, we are going to use the least square method, which will draw a best fitted line from the given data. So let's move on to the next slide and see the least square method. Use the least square method in simple linear regression, chapter 13. So chapter 13 was not included in quantitative 1. You will learn this chapter in quantitative 2 along with the hypothesis testing and parametric and non-parametric testing. So regression, you are familiar with this concept. Regression is basically used to measure the relationship between two variables. So in this chapter, we are only focusing on the line or regression line or the trend line, and we will develop the indexes. So let's move on. Code time t and use it as the independent variable. So t is basically coded as 1, 2, 3, 4. Example is given over here, that let t be the 1 for the first year and 2 for the second year and so on if the data are annual. So if the data is in an annual shape, so we will going to code first year as 1 and second year as 2 and up to till the last year. So t is independent variable in this situation. So let's move on to the next slide and see the example. So this data is going to used in a linear trend by using least square method. The sales of Jensen Food, a small grocery chain located in Southwest Texas, since 2002 are, so data is given from 2002 to 2006. Sales are also given, these sales for each year. Years is coded as these numerical values from 1 to 5. We will run this data into Excel. We are not calculating this data manually. You will learn the manual calculation for the regression in chapter 13, and you will learn the formulas for each component in regression line. So for now, we will discuss the or observe these trend lines. Blue points are, or blue line is basically showing the actual sales point, and this black line is showing the regression line. So the equation is y is equal to 1.3x plus 6.1. So if I write the this equation in a expression form where y is equal to bx plus a. So this is the intercept value and this is the value of bx. So I'll put the values into the independent variable which is given over here, and we will get the y hat's value. So I'll put the first value into the equation, 1.3. So x is the one in first for year 2002 plus 6.1. So first y hat is going to be 7.4. So this is the calculation for y hat. If you can see the formula in the formula bar, 1.3 is multiplied by B2. B2 is basically this column, and this cell is basically B2, 1 and 2 in B column. So you will put the values one by one in each year and get the value for y hat. So we will continue this procedure until x is 5. So this is the procedure for calculating the y hat. So let's move on to the next slide. But before moving on, let's have a interpretation for this slope because it's important. So 1.3 tells us that sales increased at a rate of $1.3 million per year. So each year at the rate of 1.3 million sales are increasing. So let's move on to the next slide. So here we have the non-linear trend. So what is the difference between linear trend and the non-linear trend? If I draw a graph here for a linear trend, the data is increasing or decreasing by equal amounts, which shows into a straight line, or we interpret this line in units form. But in non-linear data, it is in a curve shape on an arithmetic scale. So this curvilinear data is interpreted in a percentages or proportions. So let's move on and see how to deal with the non-linear trends. Let me clear the slide. So here is the log trend equation. So we will use the log function to normalize the data. Top graph is the plot of the original data. This pink points or pink line is a curvy line is showing the original data points. Bottom graph is log base 10 for original data with now is linear. So we applied the log function into column B and get these log sales in column C, and these log sales are plotted in this graph, and you can see that this line is near to linear line. Using data analysis in Excel generate a linear equation. So we will use the data analysis section in Excel and we will generate the linear equation, and we will learn these calculations for regression in next lecture when we will start the workshop on Excel, inshallah. So this is the last lecture from your book. So regression output shown in the next slide. So let's see the output shown in the next slide. So this is the linear equation. So after the applying log on the sales data, the data is turned into a linear form. So this is the output for the linear equation, where you are familiar with degree of freedom, confidence interval, intercept, and t, or you can say the slope of the line. So if we interpret this equation, because in log trend equation we are interpreting the each unit into the percentage change. So if I interpret the B, so it will going to be a 0.153357 is the percentage change or in a y hat for each unit increase in T. So this is basically the equation interpretation for this particular equation. In previous or you can say in already linear data, we discussed the interpretation, but that interpretation was in units. In log trend equation, it will into the percentage. So let's move on to the next slide. I'm just go through this slide for your understanding, but it is not included. So let's move on to the next slide. So estimate the import for year 2009 using the linear trend. So this is the equation for the log trend equation, and we will put the t values for each year y hat. So you will do the same as we already done in previous slides for the calculation of y hat in linear regression. So we will find out the anti-log for this value, and we will get the original sales data for 2009. So let's move on to the next slide. So here is the seasonal variation. So if you remember, we have learned about the components of time series, which includes the cyclical trend, irregular trend, irregular variation, seasonal variation, and secular trend. So it is one of the components of time series. Seasonal variation are fluctuation that coincide with a certain season and are repeated year after year. So we have discussed the example for ice cream. When the summer season, the production or demand for the ice cream is going up, and then this season is getting cold, so it goes down gradually. So this cycle, this variation is repeated each year. Understanding the seasonal fluctuation help plan for sufficient goods and materials on hand to meet varying seasonal demands. So it's good for a farm if they have planned for these demands, to cater these demands, and available that product in a particular season. Analysis of seasonal fluctuation over a period of years help in evaluating current sales. So let's move on and see that how we can develop a index for seasonal variation. A number usually expressed in percent. We already discussed that each index will multiply by 100, and we will express that interpretation into the percentages that expresses the relative value of season with respect to the average of year 100%. So ratio to moving average method. Moving average method is already familiar. We already learned about the moving average method, but in seasonal index, there is one thing added, and that is ratio. The method most commonly used to compute the typical season pattern. It eliminates the trend, cyclical, and irregular component from the time series. So let's move on and see that how seasonal index will be computed. So here is the data for a seasonal index. Let me clear the slide. A table below shows the quarterly sales for Toys International for 2001 through 6. The sales are reported in millions for dollars. Determine a quarterly seasonal index using the ratio moving average. So each year data is given over here from 1 to 6 for season, winter, spring, summer, and fall. So we will rearrange the data into a column form. So there will be 2001 data for summer, spring, fall, and winter. Then 2002 summer, spring, fall, and winter. So this procedure will move on till 2006. So it will be easy to calculate the index when data is given into this form. So let's move on to the next slide. So here is the data is arranged into a table form, into columns basically. So the steps are given into description as well. So we will start from the first column. it shows the years, and then each quarter for each year. There are 4 quarters in each year: winter, spring, summer, and fall. Then first step, organize the time series data into column form. Okay, so here is the values for each quarter. Then in step 2, compute the 4 quarter moving total. So we will add the 4 quarters one by one. So first 4 quarter total will be this, and then we will add up next 4 quarters. So we will use the moving average method. So this second value will be this. So the next 4 quarter will be these 4 values, and the third. So we are writing the summation of these 4 values into the middle of the 4 values. So we will repeat this procedure until the last value. So if I do for the next quarter, so it will going to be this value. So 1, 2, and the fourth value is this value. So after adding up the 4 moving totals, the third step is to compute the 4 quarter moving average. So we will simply divide these totals in on 4 divided by 4. So basically I think it is writing the averages. So we will divide these totals by 4, and we will get these averages, moving averages basically. So this column will be divided by 4 because we are using the 4 quarter total. So we want the value into right front of the particular quarter. So this is the summer. So we want a value at the middle of these 2 points. So then we will do a centered moving average. Centered moving average, we will again using a moving average for this purpose. So we will add up these 2 values and then divide it by 2. So the first 2 values will be added and then divided by 2. The next 2 will be added and divided by 2. Then we will get this value, and after that we will do the same for the next 2 values, and we will get this value, and this value will be right front of the winter season. So after getting the centered moving average, we will compute the ratio by dividing each sales by centered moving average. So the step 5, we will divide the given season's sales by the specific seasonal effect. So this for summer we have 10. Let me take a darker color. 10 divided by 8.475. So we will divide each season sales by centered moving average. So we will get this specific seasonal effect from these sales. For next year, we have fall's data. So this is the 12.7 divided by 8.450. So I'll took the value which is right front of the that particular season. So this is how we will calculate the seasonal index. So let's move on to the next slide. So here is the seasonal index into a tabular form. So we rearrange the data into tables. Here is the first column is year, second winter, spring, summer, and fall. So we lost the first two values for two seasons and the last two values of the season, because we were using a moving average method. So for each quarter, this is the total for each quarter, and then we get the means for each quarter, and this is the adjusted mean for each quarter. How we get this adjusted mean? Basically, we need exactly four value here, but due to seasonal effect, we get this 4.009. So then we will use this correction factor to remove this effect. We will 4 divided by the total 4 means, and we will get this value. So the total of mean is 0.4009, 4.009. So we will put the values into this correction factor, and we will get this 0.997755. So after that, we will multiply this value with these means one by one, and we will get the adjusted mean. So if I write here 0.767 into 0.9978, so approximates it. So then multiply these two correction factor and mean, it will be turned out into adjusted mean 0.765. So then we will multiply this value into 100, we will get the index value. So that is the 76.5%. So this is the calculation for seasonal index. In next slide, so actual versus deseasonalized sales for Toys International. So how we will deseasonalize the sales? We will simply divide the sales, original sales or actual sales, by the seasonal index. So let's move. This is the first column is showing the sales data, second is showing the seasonal index, and third is showing the deseasonalized sales. If you can see, we have repeat the quarterly adjusted means for each year. So it is quite simple, but a bit lengthy procedure for calculation the seasonal index. So let's move on to the next slide. Here is the actual versus deseasonalized sales for Toys International time series plotting by using Minitab. Minitab is a software which is used for the data analysis or statistical analysis. So this column C1 is showing the years, C2 is showing the quarters, and then they coded the quarters for plot on a graph. So next is the sales data. C4 and C5 is showing the index, and C6 is showing the deseasonalized data. So red points are showing the deseasonalized data without seasonal effect, and these black points, connected points, are showing the actual sales. So you can see the variation into the data, or seasonal effect into the data, and then after deseasonalizing the sales and removing the seasonal effect from the sales data, it turned in a small variation into the data. So let's move on to the next slide. Seasonal index using Excel. So this is the Excel calculation for seasonal index. Hope we will do this also. Then we will discuss this example at that point. So let's move on to the next slide. So again, this is the output from Excel's data. The previous one was the Minitab output, and this is the Excel output. The same example, this blue line is showing the seasonal variation for actual sales, and this pink line is showing the deseasonalized data, or you can say this is the sales data without seasonal effect. So on vertical column you have sales, and horizontal axis you have quarters for each year. So after calculating the seasonalized sales, this is the equation for this pitted line, and R square is basically the coefficient of determination which measures the strength of relationship between two variables. So let's move on to the next slide. So we got the this equation, and now we can calculate the next year quarters. So we have the data till 2006, and the last quarter was 2024. In 2007, winter quarter will be coded as 25, next 3 quarter till 28. So we will put those values into this equation, and we will get the unadjusted forecast. So this is the calculation for 28. We will do the same for the previous 3 values. And we also have the calculated seasonal index values for each quarter. We will simply multiply unadjusted forecast and seasonal index. So we will get the quarterly forecast and seasonally adjusted forecast. So this is the seasonal index, and in next slide we have Durbin-Watson. So we are not going to discuss this topic as it is the part of your quantitative 2 course, and we are completed our syllabus for this semester. We are only left with two lectures, and as promised we will do Excel exercises in those 2 lectures. And thank you so much. Allah Hafiz.